All right, we want to do hypothesis testing on our beta hat, or well, really on beta. Um, Now, so we'll first look at if we use a t-distribution. Um, so suppose we have H0 null hypothesis that our beta is equal to some beta 0. And then the alternate is a two-sided test that says beta is not equal to beta 0. Okay, in this case, we can get a t statistic um, with n minus 1 degrees of freedom by taking our beta hat minus beta 0 over the standard error of beta hat. Okay, so we compute it that way from our standard error and so forth. And then we just check. We look for the probability. So we'll call this little p is the probability, our p-value, that the absolute value, that t minus 1, is greater than or equal to the absolute value of our b hat minus b0 over standard error of b hat. Now see, there's kind of a problem with notation in that that's our t statistic, so maybe I'll call that t hat, because then this is just the general t distribution. So we look at that p, and if p is less than alpha, then reject H0 in favor of the alternative. And if p greater than alpha, fail to reject H0. Okay, so that's a hypothesis test for this thing. Now, typically, we use beta 0 equals 0 for our HA, or sorry, HO, our null hypothesis. Okay, and the reason for that is, this is to check independence versus dependence of our variables x and y. Because typically that's what we're interested in. Is there a dependence or not? And then if there is a dependence, what's that model? And so we would want to know what our b hat would be. And so, in this case, H0, beta equal beta 0. Gosh. Now let me just rewrite that so it looks a little better. Okay, beta equals 0. So, in that case, we have independence. Okay, because again, that would be a slope of 0. So we would see data that look like that if that's x and that's y, and yeah, I can't predict y any better by knowing x. But then HA is beta not equal to 0, and so that's dependence, because in that case, if I'm looking at X and Y, then, I'm seeing data that do something like that, and if I know X, I can do a better job of predicting Y. And so that would be the dependence. So it really comes down to, is that slope 0 or not 0? And so that's typically what you're going to see for this kind of hypothesis test. So in that case, what we're looking at is our t n minus 1 is equal to simply the beta hat over the standard error of beta hat. Because, right, B0 here, or beta 0, is 0. And so we just get that for our t statistic that we would look up. Okay, so that's a t distribution. Now, we can also use an f distribution. We end up getting the same exact p-value. So really, for this case, the one parameter case, these are actually the same test. However, with the f distribution, we're always doing H0 is that beta equals beta 0. Beta 0. Try that again. Is equal to 0. And then HA beta is not 0. So with the f distribution, I can't, at least as far as I know, I could be wrong, but as far as I know, I can't check anything but the independence and dependence, whether beta is 0 or not. And so this is, in this case, we have degrees of freedom. Degrees of freedom are 1 and n minus 1. So it takes 2 sets of degrees of freedom on the f variable. And so what we're going to do is look at variances here. And so what we call this is an analysis of variance. And if you hear the word ANOVA, I guess it's just one, not to the A, it's just to the N. ANO and VA, ANOVA, analysis of variance. So here, notice that if I take the sum of the yi minus y bar squared. Okay, now in our assumption is that that's 0. Okay, because if beta is 0, our model is simply that y equals that error, which, remember, that had a mean of 0. And so this is just the sum of the yi squared. Okay, in this case, because we just had that mean of 0. And so we get the sum of the yi's. Now, if I take that and I play with it a little bit and I say, well, that's yi minus yi hat plus yi hat squared, then that is the sum of the yi's minus the yi hat, so squared. So this would be the sum of the squares of the residuals. Then we'll get plus, I'll put it down here, so 2 times the sum, so that middle term will be yi minus yi hat times yi hat. Okay, and then plus the sum of the yi hats squared, and this we call the sum of the squares of the model. Okay, now this is 0. So we'll put a little arrow there. That's 0. And so we'll get back to that in a minute. But so our F distribution, our F1n minus 1 tilde, is equal to the sum of squares of the model over the sum of the squares of the residual. And if, and then we check the probability, so in this case, our p-value is the probability that f1n minus 1 is greater than or equal to the sum of squares model over sum of squares residual. And that's our p-value. And so again, we, if p is less than alpha, reject H0, and if p is greater than alpha, fail to reject H0. So that's what we get with the sum of squares in the analysis of variance. Now, let's look at that. So we have 2 times, so forget about the 2, because if it's 0, 2 times 0 is 0. So we have the sum of the yi minus yi hat times yi hat. Okay, the model. That then is the sum of the yi hat minus the sum of the yi hat squared. Well, so this is the sum of yi, and then yi hat, that's beta hat times xi minus the sum of beta hat times xi squared. So this is equal to beta hat times the sum of the xi yi minus beta hat squared times the sum of the xi squared. Now, beta hat, remember, the way we calculate that is that's the sum of the xi yi over the sum of the xi squared, and then that's times the sum of the xi yi minus, and so we've got the sum of the xi yi all squared over the sum of the xi squared times the sum of the xi squared. And so we end up with the sum of the xi yi squared over the sum of the xi squared minus, and here we have the sum of the xi yi squared over, and we've got xi squared sum there over the square of that, so we just get one of those, xi squared, and so we see that's 0. So that is indeed 0 way back here, so that just goes away, and so we just get those sums of squares. So the total sum of squares here, so we would tend to call this sum of squares total. That is equal to the sum of squares residual plus the sum of squares of the model. And so we just look at those two things, and if the sum of the squares of the model divided by that sum of the squares of the residuals is really small, small enough, that's going to actually give us a big p-value, and so that's kind of what we're looking for, is if sum of the squares of the model divided by sum of the squares of the residual is small, whatever that means for our degrees of freedom, then we'll fail to reject H0. Let's reject H0, and so we'll assume that these are probably independent. Okay, between x and y, and if that's big, so if the sum of squares is large, then reject H0. In that case, we think there is a slope, and so there's dependence. Okay, so we have two different ways we could do that test. We could use a t distribution or an f distribution. And so that is what we call this analysis of variance, or ANOVA. That's using the f test and the sums of squares. Or we can just look at the slope and a t-test and do the same thing that way. So we have two different tests for this.